Hello, assalamu alaikum.
Alaikum salam.
Salam.
Okay, bismillah ar-Rahman ar-Rahim. Last time we are doing chapter number 3 and the system of linear equation. And last time we finished the direct method for solving the linear system. Today we will talk about iterative method for solving a linear system. I give some basic idea about the iterative method for solving the linear system last time. And let's we start here because iterative method, one of the best numerical methods to deal with the linear system, especially when you have the size of the system is very large. Direct method are not suitable for the large linear system. Iterative are the best one in the iterative, but we have to do a lot of things. As I mentioned you last time here, we have to check the initial approximation, we have to check the stopping criteria, we have to check the convergence of the method. If converge, we have to check slow or the fast convergence, right? So remember, as I give you the last time, the basic idea of the first iterative method, which is a Jacobi iterative method. And I told you this is one of the best, not best, sorry, one of the simplest iterative method. And simplest always being is not a very nice one, but easy to start always. And I give you the first condition for the iterative method. Your diagonal element should not be equal to 0. And we have here now. This should not be equal to the 0. And then if this not happen, then we can find out the Jacobi formula for x1 from the first equation, Jacobi formula for x2 from the second equation, Jacobi formula for x3 from the third equation. So how can you find the formula? Take all the term on the remaining term on the right hand side, like this one you take here, and you have the shape like this one. And from the second equation you can find out x2, and from the third equation you can find out x3, and take all the term on the other side here. And then you can divide your diagonal element. Therefore, I told you the diagonal element should not be equal to 0, because if the diagonal is 0, it comes in the denominator, and we always say denominator should not be equal to the 0 we have here. So we find the value of x1 and the x2 and x3 from the first equation, second equation, and third equation respectively. Then we need the initial approximation. Always we need the initial approximation for the iterative, and initial approximation must be given always. So we have this one. And then use this initial approximation on the right hand side. This is the initial approximation for x1, for x2, and x3. So we can have here, and I just put the value there. And when you put the initial value on the right hand side, the left hand side is your what? Is a new approximation we have. And this is called simplest Jacobi iterative methods we have for solving the system of linear equation. And this is a particular case. This is a three linear equation for the system we have here. Very simple one. Formula for first variable from the first equation, formula for second variable from the second equation, and the third variable from the third equation, like this. And this is, I give you the last time, the generalized shape of the Jacobi method for the system of n linear equation, system of n linear equation we have. Now let's take now, this is a stopping criteria, as I told you here. That means the new approximation which you calculated. This is the old approximation or initial approximation given by the teacher. And this is the accuracy. If teacher not mention you by number of iteration, he give you the accuracy always. Then we say the difference between these two is less than accuracy, stop, otherwise continue. This is also the another way to use accuracy, but generally we use this formula. If teacher mention you accuracy, then you have to use, unless teacher say use this way here. Otherwise, always use this one here. And you have to find this, and then take the difference between them, and then you take the L infinity norm. Remember we discussed last time the norm of a vector. And what is the L infinity norm of a vector? L infinity norm of a vector is the maximum element in the absolute sense here. Okay, let's start with the first example. And of course, from examination point of view is not suitable because they give you some very good accuracy, and good accuracy mean Jacobi, I told you, is not a very nice method. And if you want to use Jacobi method to get the good accuracy, we have to use the formula many times here. Anyhow, let's say I give you the general idea of the Jacobi methods. He said find the approximation of the solution of the system with the help of Jacobi method by using initial approximation, this one, and by using stopping criteria is this one. So first your job is what? You have to find the value of x1 from the first equation, which is you can easily find out value of x2 from the second equation, and you will easily find out this one, and value of x3 from the third equation by taking this one on the other side and putting the initial approximation symbol, and you have this shape here. This is a Jacobi formula for the given system now. Now you are ready to use the formula, and you are given initial approximation. Initial approximation for x1 is 0, for x2 is 0, for x3 is 0. It is not always for the all system, but this particular system, the initial approximation is given 0. Now let's have used this one now, please. And this is the initial approximation given now. Now you use in the formula, you put the first approximation you have to find out. Just put in the formula k equal to 0. When you put k equal to 0 for first case, so you have your x1, the first approximation for first variable, and you use this formula 1 over 5, 10, and x2 0. And what is x2 0 given? X2 0 is given by the teacher is a 0. And what is x3 0 is given? It's also given 0. Just put the value here. So you left with what? 10 divided by 5. So your first approximation for x1 is a 2 here. Similar way you can use for the second variable, and you use initial approximation for x1, which is given 0, and x3 given 0. So you can have 11 over 8, which is 1.37. And similar manner, you go for that one here. And this is the things you have the first approximation here. Now you have to check this accuracy. This is the things you find out. What is your first approximation you find? 2, 1.375, and 0.5. And your initial approximation given is 0, 0 here. Can you give me, we know epsilon is a 10 here. This is, you know, you just calculated. This is given by the teacher, 0, 0, 0. And this is you calculated is what? 213.7. What is the L infinity norm here, please? Any student? I give the last time the definition of the L infinity now. You have the formula, the norm, L infinity now, which we call it x11, which you just calculated, and x0, which is given by the teacher, and the norm. And the condition of the norm is given 10 minus 6. If the difference between x1 minus x2 is less than 10 minus 6, then stop, otherwise continue. What is your x1? Your x1 is the first approximation, 2, 1.375 and 0.7. What is your x0? It is given 0, 0, 0. What is the L infinity norm now, please, you have here? Any student? What is the difference between x1 and x0? First of all, you tell me. What is the difference between x1 and x0?
2.
No, the difference is this minus 0, this minus 0, this minus 0, right? So it's mean this is 0, so only we left here. So now we have to find out L infinity norm of this one. And what is the L infinity norm, please? L infinity norm of a vector is the maximum element in absolute sense. So what is the jawab? Is it 2? And 2 is not less than 10 minus 6. So we have to continue. And how you can continue? Now you put in the formula k equal to 1. When you put k equal to 1, what you have here now? x12 equal to 1.510 plus x21. And what is x21? You just find out is 1.375. And what is x31? You just find out 0.75. So same way you can get, and you will get the second approximation, and then check the second approximation minus first approximation is less than 10 minus 6, stop, otherwise continue. I give the jawab in the form of table. This is given the initial approximation. This is the first time you use the formula. This is the second time you use the formula. First, you check the difference between the second one and this one and this one is less than 10 minus 6, stop. What we check is 2. Then you check the difference between this is less than 10 minus 6, stop, otherwise continue. No, it is not less than. This means we have to continue. And we continue up to 16 iteration, and we stop here because the difference between difference between 16 and 15 is less than 10 minus 6, so we stop here. So you can see here the Jacobi method, very simple method to use it, but it's not a very good faster convergence method, because to approach to the accuracy 10 minus 6, we have to use the formula. How many times we have to use the formula? 16 times, and 16 times is too much we have here now. You understand, please, Mike? Any question you have up to now, please?
Clear.
Is okay now. We have the second example. So it means we solved the first example, and alhamdulillah, Jacobi method converge here. And we take another example. We have 2x1 in this, and then you can find out the same way formula for x1 from the first equation, formula for x2 from the second equation, formula of x3 from the third equation, and then you can work on that one here. Use the same accuracy here, and inshallah, because he says start with this one here. And then he says the result of this example is given table 3.2. This is a result given here. Now you can see something is going wrong here, because first approximation for x1 is a 5.5, x2 is minus 10, and x3 is a 0.75. We don't know this is good or not good, because we don't know the exact jawab. The exact answer we don't know. So what we have to do, we have to find the second approximation, and the difference between first and second should not be too much. If something is too much, it means something wrong. And the wrong is the method is going in the direction which we are not interested. That means it is diverged. You can see when we use the second time formula, we have a very big difference between the previously and the new one here. And when you use the third time, so we have big change from here to here. It means something wrong, and the wrong is Jacobi method for that system is diverged. So now we have a simple idea, simple rule for the Jacobi method is what? Jacobi formula for each variable of a vector can be obtained from the respective equation, x1 from x1 from first equation, x2 from the second equation, and continue. Then Jacobi method, after having the formula, then you can say something about Jacobi method. Jacobi method may converge, may diverge. It is not always converge, but if it converge very slow. Right. So now, as I told you, we have to use a two iterative method for that case here now. And how I check this is converge? Because you can see the difference between the approximate value each time is getting not big difference between them. Therefore, we say we are in the right direction. Same like in chapter number 2 we did. But here we can say here is a big difference here. So of course, very soon I will give you one condition. That condition we can say here the method will converge or not. I don't know you remember or not. What is the condition of the chapter number 2? The method is converge. Any student know? The condition of the convergence of the chapter number 2, we say g dash at alpha, if this is less than 1, then we say the method always converge. Greater than 1, always diverge. Equal to 0, converge very fast. Equal to 1, no guarantee, may converge, may diverge. If converge, very, very slow. That's the condition. The same condition I will give you, inshallah, very soon for the case of the system of linear equation for the chapter number 3. Up to now, you know that if the difference between the approximation is coming smaller and smaller, it means we are in the right direction. Right direction means the method converge for that case here. Otherwise, we say no. Now, let's say we discussed two systems. This system, Jacobi method converge, and this system, Jacobi method diverge. Well, we leave this one because it's a diverge here. But for this system, Jacobi method is converge. But it converge very slow. Let we make small change in the Jacobi formula to make it faster convergence. You remember that one? We solved this example with the accuracy 10 minus 6. How many iteration we took? Is a 16 iteration, which is slow. We make small change in the Jacobi method to make it faster here. Now, I repeat again, the procedure of the Jacobi method is what? The formula for x1 from the first equation, formula x2 from the second equation, formula of x3 from the third equation. And then we use the initial approximation from the right-hand side, and we find the jawab this one. Then we use the first approximation on the right-hand side. We have a second. And then second use on the right, third, and continue like same manner. Now, we make small change to make it faster. We start with the Jacobi formula, which is this one here. We are given this initial approximation. So your first job is to find out first approximation of x1. What is the first approximation of x1, please? What is the first approximation of x1?
2.
The 2. Just stop here. How many approximation you have for x1 now, up to now?
Only one.
One is given by the teacher, right? And one you just calculate. So how many you have now?
2.
2. Good, very good. How many approximation you have up to now? I'm only working on the first equation. How many approximation for x2?
Only one.
Only one. How many x3? Only?
One.
One. Now we move to the second formula. And in the second formula, we need x1. And this x1, we will not use the initial one. We will use just new one we just find out here. You understand me? We will
Yes,
not,
yes.
we will use, and what is the x3? We have only one initial one, so no chance. So we will find out x2 1 is what? 1/8, 11, 2x1, 1, which we just calculate on the same step, which is 2, not we use 0. Jacobi say use 0, but not here. So we have this one. Now when we find x3, we need x1, and we know x1 should be the new one, which is 2. And we also have the x2 new one, which is 1.375. That is a small modification we make in the Jacobi formula. Jacobi formula say in the first step only use initial approximation, second step only use the initial, first approximation, and third use the second. I continue. But modification we make it as we have the new approximation of the variable we use in the same step, not the initial Qadim one, Jadid one we have to use here. Can you give me here, when you make this change, this formula will be changed. What will be here, please?
K plus 1.
Yes, it is k plus 1. This is the same thing here. This is same. It will be k plus 1, and this will be also k plus 1, because we just have x2 k plus 1 in the previous line here. And this modification is called a new formula, which we call the second one called Gauss-Seidel formula. And the Gauss-Seidel formula is what? This formula is a modification of the Jacobi method and give a good accuracy by using what? By using the most recent calculated value. Like this one, the formula is what? This is a Gauss-Seidel formula, very simple one. X1 from the first equation, X2 from the second equation, X3 from the third. But here, when we find X1 k plus 1 from the first step, and we use X2 in this here, X1, so we use the new value of X1, which is a k plus 1, not k. K is the initial approximation given by the teacher. And this is the formula for n linear equation. Let's redo this example, exactly the same example which we use here for the case of this one. I use the same one again. So 339 method converge slow, 340 diverge. Diverge, we leave it. Now we use the same 339 as a new example, and I call it 341, exactly the same condition, accuracy is the same here. So first you have to find the Seidel formula, and the Seidel formula is this. We have this one. This is your formula, Seidel. Only change is coming what? Seidel formula and the Jacobi formula for first variable exactly the same. Change only coming in x2, x3, x4, x5, whatever you have the size of the system. Now you have to put the same thing, use initial approximation given by the teacher, which is 0, 0 here. Put k equal to 0 here. And first you find x1 here, so you have 10. X2, 0, you have only one initial approximation. X3, 0, only one initial approximation. So you find out the first approximation for x1 is a 2 here. When you use to find x2, you need x1. So x1, you use the first one, the new one we just calculated here now, which is 2 here. This is the initial which is given here 0. So we have 2 multiplied by 2 is a 4. So 7 by 8 give you this one, and we have to find x3. When we find x3, we have to use the new value of x1 and x2, which we use here. And this is 1 by 4, 3. x1 new value is 2. And x2 1 new value is 0.875. And that's the new first approximation by Gauss-Seidel. And we continue like the same accuracy we check here. And when we reach this one here, we can approach to the accuracy 10 minus 6, and we use up to 10. 10 is not very good, but it is much, much better than the Jacobi method, because we know Jacobi method for this formula took how many? He took 16 iteration, and Gauss-Seidel took only the 10 iteration, which better than that one here. And I solved the second system, which we solved by the Jacobi method, and we already checked is the method is diverged. We use the same system again for the case of Jacobi method, which is exactly the same. And we also check here the problem coming here again, and that is mean the Seidel method also diverge. It's mean the small modification in the Jacobi only give you guarantee what? Slow converge to the faster, but he never give you a guarantee that if it is diverge, become converge. Maybe, not, no guarantee for that. So it's mean Jacobi method and the Gauss-Seidel method maybe converge, maybe diverge. For some system, both converge. For some system, both diverge. For some system, only one method converge, other does not. We don't care about the two type of the system where both diverge. We will not consider. We will not consider such system where one method converge, other not. We will not consider. We only consider in our discussion such system where both methods converge, and then we have to check or show the Gauss-Seidel method converge faster than the Jacobi methods we have here now. I give many examples here. This is the things that we have here now. Please, this is the note you have to remember, which I mentioned here. I say in general case mean about 99.99 case, if the both the Jacobi and the Gauss-Seidel method are converged for the given system, then Seidel method converges more quickly. But this is generally the case. Generally case mean 99.99 case, but not always true. In some system, but very few system, they converge almost same way. Almost same. Okay. And also, as I told you, there are some system, linear system, where Jacobi method converge, but Seidel does not. Another Gauss-Seidel converge, but Jacobi does not. But we not discuss here. I give this system here. No need for that one here. Now, before I give you the condition for the convergence, as I told you, what is the condition of the convergence? The condition of the convergence for the linear, for the chapter number 2, I told you is what? The G dash absolute is less than 1. There, then we say method converge. Same type of the condition we also need here in the case of the Jacobi methods we have here now. And the Gauss-Seidel. So first things we have to do here, how can we find out the Jacobi formula and Gauss-Seidel formula in the matrix sense, in the matrix form? So we are given iterative system, iterative method for the linear system, and this is a linear system. And this is also the shape of the linear system, but this is a shape, this one and this one exactly the same. This is linear system for generalized case. This is linear system symbol only for iterative case we have here now. So what we have to do here, because you remember that one here, in the iterative method, we need initial approximation. So what is this one? We call this is initial approximation given by the teacher, and this is the new approximation you have to calculate. This is the formula I give here now. This formula is called iterative formula for the linear system. And this iterative formula may be for Jacobi or maybe for Seidel, depend on the value of T and C here. And thus we can find out here how to find the value of T and C for the case of the Jacobi and the Gauss-Seidel method. We have to decompose A into the form of L plus D plus U. L is a lower part of the matrix, D is a diagonal part of the matrix, and U is a upper part of the matrix. And of course, when you take L plus D plus U, it will exactly give you the A we have here now. Let's say give you the value for the Jacobi case. And for the Jacobi, please, this is called Jacobi iterative formula in the matrix form. That is a very important formula. Please remember that one. It means you need to calculate what? You have to find Tj and Cj. Tj means the iteration matrix for Jacobi, and this is a constant we have here, and that formula is important also. That how to find Tj, this is the formula. D inverse, you know what is D? D is a diagonal part of A. What is L? Is a lower part of A. What is U? It is the upper part of A. And this is your C, the constant term we have here now. Remember that one, when you find Tj, this is a very important point. When you find the matrix Tj, the diagonal element of Tj for any system must be 0. If you are not getting 0 in the diagonal, it means something wrong with your calculation. You have to recheck your calculation for this formula. In the same way, you can get the matrix form of the Gauss-Seidel formula, which is, this one is a matrix form of the Gauss-Seidel. Here you need Tg and Cg, and this is the formula you have to memorize here. This is the formula of Tg, L plus D inverse U, and this is the formula for Cg. So this is a two important formula for the, how can teacher, maybe teacher say, write the given system in the form of Jacobi or Gauss-Seidel in the matrix form. So it's mean you have to calculate the Tg, which this formula for the Seidel, and Tj, which I told you. Now leave this example 3.45 is not with us here. This is the things now we are ready to use the convergence criteria of the iterative method. Convergence criteria of iterative method mean when your iterative method converge, when diverge. So the first condition for the convergence is a very simple, which generally teacher never asks you in the exam here. And that condition, you remember last time we did STD, strictly diagonally dominant. If your matrix is strictly diagonally dominant, then it is 100% guarantee the both method, Jacobi and the Gauss-Seidel method, guarantee converge. And for STD, you don't have to do anything. Only you look the system and you can see it is STD. I don't know, you forget last time I gave you the idea of the STD. STD means all the diagonal element in each row, respective row, must be bigger than, in absolute sense, some of the other element of that row. I don't know, you can tell me this is STD or not? Any student, this is STD or not? This is the first time I have such group in my life here. Very, very bad student you are. Wallah. I just give you last time here the condition for STD here. Go back here. Where STD? This is condition for STD here. If all the diagonal element is bigger than in the rest of the element, 7 is bigger than 4, 6 is bigger than 4, 8 is bigger than 6, we say STD. If it is not, we say not STD. 6 is bigger than 7? No, it is mean this matrix is STD and this one is not STD. Yes, I give this problem in the exam here. So condition for the convergence is what? If your system is STD, your system STD mean the coefficient matrix of that system is STD, it is 100% guarantee the method will converge. Now, I give this example. First of all, can you give me if this is STD or not?
No.
No. And when your system is not STD, we have no guarantee may converge, may diverge. The question given in the exam, I give many times this example in the exam. I say rearrangement your system such that the convergence of the iterative method, Jacobi or Seidel, is give you what? Guarantee they converge. When teachers say rearrangement your system, it is 100% guarantee. He give you the system is not STD, you have to make STD. How can you make STD? You have to play with it, rearrange it. So the only one things you can do here, take your last row as a first row or first equation. You will get this shape of things now. Is this one STD or not?
Yes.
It is STD. Now it is guarantee here for the convergence. The convergence of the guarantee is what? Should be STD. Strictly diagonally dominant. And now when it is STD, now you can say here, I asked to find out the first approximation or the second approximation. And that you can do the formula from the first equation, and that you can do here. This is the second condition, but STD, only you look the system and you can say this is STD or not. If it is STD, you say the method will converge, guarantee. But if it is not STD, we don't know, maybe converge, maybe diverge. But when it is STD, definitely guarantee they converge. But when you remember why we know if we have method converge, we have to check converge slow or fast. But STD never give you any idea is slow or fast. He only give you the condition converge or not. But we want, if converge, it should be slow or fast. That we cannot do with the help of the SDD condition. We need the second condition, and second condition is one of the the best condition we have here now. And what is second condition here is this one. He say for any initial approximation, this is what? This is, I told you, the shape of the iterative formula in the matrix sense. All the iterative method, both iterative method, the Jacobi and the Gauss-Seidel, converge guarantee to the linear system. If this condition true, this condition, this is a condition we have here now, please. And what is the condition? The norm of t should be less than 1. And that's condition. And norm of t is less than 1 mean if it is between 0 and 1, the norm of t, definitely the method will converge. If not, we have no guarantee, may converge, may diverge. If it is close to 0, method converge very, very fast here. And this is the error bound formula of the iterative method. Maybe for Jacobi, depend on t, or maybe for Seidel. This is initial approximation. Sorry, this is initial approximation, and this is the first approximation we have to find. So this is a two condition. I give many times this example in the exam here now. We do this one, then we continue next time here. He say, consider the following non-homogeneous linear system. Find the matrix form of the Jacobi and the Seidel method, and show that the Gauss-Seidel method converge faster than the Jacobi method. So this is your given. You have to show this one. The norm of TG should be smaller than the norm of TJ. First, you need to find out the norm of TJ. So to find norm of TJ, you need to find TJ. What is the TJ formula I give you here? It is minus D inverse L plus U. D is the diagonal part of A. L is the lower part of A. U is the upper part here. So what is your A given? This one. What is the diagonal part? 5, 3, 4. We have this one. And what is the lower part? Minus 1, 0, minus 1, and 0. This is the lower part. And what is the upper part? 0, minus 1, and 0. So we have this one here. And when you multiply, you find the inverse of D. Inverse of D is a very simple. Inverse of every diagonal matrix is a reciprocal. What is the inverse of this one? 1 over 5, 1 over 3, 1 over 4. Simply, no need to calculate inverse. You multiply this together and you get, this is a TJ norm. TG matrix here. And you remember that one here. After finding TJ, you can find TG also, CG, and CJ, inshallah. We know what is the formula of, I give you what is the formula of the constant for the case of Jacobi. If you remember, I give is a D inverse into B. B is given 1, 2, 4, and D inverse, I told you, what is the D inverse? 1 over 5, 1 over 3, 1 over 4. When you find this one, inshallah, you will get, this is your C, and this is your TJ, and this is the formula of what? This formula is for the Jacobi method in the iterative form, because he's saying matrix form. Find the matrix form of both methods, and then we do the same thing with the help of this one. This is the Seidel. We have minus D plus L minus U, and that you find the inverse. And when you simplify, you have, this is the TJ, And this is CG, and this is a matrix form of this one you can find. So we finished the first part. The second part, he say, show that the Gauss-Seidel method is converges faster than Jacobi. The faster than Jacobi, we have to find this one. What is the norm of TJ? We know what is the TJ. TJ is what? TJ is this one. What is the norm of TJ, please? L infinity norm. Do you remember LT norm? What is the L infinity norm of a matrix? L infinity norm of the matrix. If you remember last time I discussed the sum of the element of each row in the absolute sense, and then maximum the row. Is who's that one, a student? He's a sleeping what? Oh, who's that, a student? He almost sleep. I think here is taking showing here. Who's this one here? Let's check. Whose mic is on here? So we have the TJ norm. This is first row is 1.5, second row is 1/3, and third row is 1.4. First row is 0.2, this is 0.33, and this is 0.25. So its maximum is 1/3. So this is the things you have here, 0.33, and the same way you have, this is your TG, maximum of this one. And first row is 1.5, second row is 1/15, third row is 1/60, the maximum is 2, and we have is a 0.2. And which one is smaller? TG is smaller, and smaller the norm, faster the convergence of the iterative method. It means your iterative method is converged faster than the Jacobi methods. We continue, inshallah, more about this one on next time here. Any question you have, please, if you are not sleeping.